Hello everyone, I'm Jalraj Analaki Manimaran. My matrix number is 241110924. I'm here to present about the Reynolds transport theorem. The Reynolds transport theorem (RTT) is a fundamental principle in fluid mechanics that bridges the gap between two perspectives of analysis, which is the system approach and the control volume approach. The system approach tracks a specific group of particles over time, while the control volume approach focuses on a mixed or moving region in space through which particles and properties flow. It is widely used in engineering and science to study the behavior of fluids, control processes, and energy systems by accounting for both the changes within the control volume and the flux of properties across the boundaries. As you can see here, there are diagram A and diagram B. Two methods of analyzing the spraying of deodorant from a spray can. From diagram A, we follow the fluid as it moves and deforms. This is the system approach, which is no mass crosses the boundary and the total mass of the system remains fixed. For diagram B, we consider a fixed interior volume of the can. This is the control volume approach, which is mass crosses the boundary. The relationship between the time rates of change of an extensive property for a system and for a control volume is expressed by the Reynolds transport system. The Reynolds transport theorem provides a link between the system approach and the control volume approach. From the diagram given, there are two parts, which is hatched region and shaded region. The time rate of change of the property B of the system is equal to the time rate of change of B of the control volume plus the net flux of B out of the control volume by mass crossing the control surface. From the equation, which is dB system over dt equals to dB CV, which is control volume over dt minus B in plus B out. This equation applies at any instant in time where it is assumed that the system and the control volume occupy the same space at that particular instant in time. A moving system, which is hatched region, and a fixed control volume, which is shaded region, in a diverging portion of a flow field at times t and t plus delta t. T represents time and delta t represents changes in time. The upper and the lower bounds are streamlines of the flow. We represent any extensive property such as mass, energy, or momentum, and let B equals to B over m represents the corresponding intensive property. Nothing that extensive property and additive. The extensive property B of the system at times t and t plus delta t is expressed as the equation below. From that, subtracting the first equation from the second one and dividing by delta t gives us the equation below. Taking the limit as the delta t to the 0 and using the definition of derivative, we get the equation given below. From the diagram given, we can see that it's a control volume, which is mass leaving and mass entering, and its equation is given. The integral of bpv dot n dA over the control surface gives the net amount of the property B flowing out of the control volume, which is into the control volume if it is negative, per unit time. The outflow and inflow of mass across the differential area of a control, and its equation is as given below. There are three equations shown in the diagram or the slide, which is relative velocity, RTT, non-fixed control volume, or and RTT steady flow. From the diagram shown, Relative velocity crossing a control surface is found by vector addition of the absolute velocity of the fluid and the negative of the local velocity of the control surface. Reynolds transport theorem applied to a control volume moving at constant velocity. As we can see, there are diagrams given below of a car V-jet and V-car. Relative reference frame control volume, which is VR equals to V-jet minus V-car. As the slide shows, the equations are given for the approximate RTT for well-defined inlets and outlets. From the diagram, we can see it is an example control volume in which there is one well-defined inlet 1 and two well-defined outlets, which is 2 and 3. In such cases, the control surface integral in RTT can be more conveniently written in terms of the average values of fluid properties crossing each inlet and outlet. In conclusion, the Reynolds transport theorem is a powerful and versatile tool in fluid mechanics. It establishes a clear connection between the system and control volume approaches, enabling the applications of fundamental conversion laws, which is mass, momentum, and energy, to real-world engineering problems. That's all from me. Thank you.